Good morning, good afternoon, or good evening, folks. I hope you're doing very well. We'll jump into the lesson in just a moment, but before we do, I wanted to say that I hope you're doing well. I hope you're taking care of yourself. I hope you're washing your hands, right? Also, I want to let you know that I miss you guys very much. It's just not the same recording these lessons without having you all near me to talk to. So I do miss you guys. I hope you're taking care of yourself. As always, I very much appreciate those of you who are checking out the lessons and doing the follow-up activities. I try to offer feedback as quickly as possible. If you have any questions, please, 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 please don't hesitate to email me. Some of you have been. I appreciate that very much. So we'll all come through this on the other side, and we'll see each other again. But I just want to let you know that I do miss you, and I appreciate everything that you're doing. And take care of yourselves. I'll talk to you later. Bye. Okay, everybody, today we are talking about energy, and we're starting on Unit 6. Our first lesson is called Energy and Work. Let's start with getting a definition for energy. Energy is one of those things that's kind of hard to define. It's like the wind. We can see the effect that it has on things, but we cannot see the wind itself. And energy is sort of the same way. You cannot see it, taste it, smell it, hear it, but you can measure the effects of energy. Simply put, energy is the ability to do work or to cause change. Anytime you cause an object to start moving, stop moving, speed up, slow down, change direction, change shape, change temperature, any of those things will involve the movement of energy. How do we measure energy? Well, using the very basic units, energy is equal to kilograms times meters squared per second squared. And this looks similar to the unit for force, which is kilograms times meters per second squared. So this is like taking the unit for force, which is a Newton, and multiplying it by one more meter. So we can also measure energy in Newton meters. Now you may be looking at this and thinking, that's the same unit that we use for torque. Well, it does have the same dimension, but it's not the same unit. And the reason is that with torque, the force needs to be at a right angle to the radius. So these two dimensions are actually in different directions. In energy, the newtons and meters have to be in the same direction. So this is actually not the same unit. No, you cannot use the third unit, which is a joule. You cannot use joules for torque. You have to use newton meters for torque. But for energy, when the newtons and meters are in the same direction, then you can substitute a joule, which is abbreviated capital J. A joule is the same as a Newton meter, which is the same as a kilogram times a meter squared per second squared. Now we need to point out here that energy is a scalar quantity. That means it has no direction. So when you're measuring energy, you don't have to say 32 joules north or positive 16 joules or negative 18 joules. It's a scalar quantity, so directions don't matter. Now there's many different forms that energy can take, and we could sit here all day and not list all the possible manifestations or forms of energy. So it's best to just sort of lump them together into some easy to remember categories. And you can remember the phrase I scream, like this guy here. I stands for internal energy. This is energy of like temperature. S is for sound energy. C is for chemical energy. This is the energy stored in the bonds between atoms. R stands for radiant energy, which is like another word for light. E for electrical energy. A for atomic, or sometimes called nuclear energy. And then M is for mechanical energy. And we'll be spending a lot of time talking about mechanical energy in depth when we get to Unit 6.3. There's a very important concept when we talk about energy called the law of conservation of energy, which says that the amount of energy in a closed system is always going to be constant. Now, energy can transform, it can change from one form to another, but as long as no energy is allowed to escape or enter this closed system, then the total amount of joules inside the system has to be the same. So For example, if we have this battery powering this light bulb, the energy starts off as chemical energy stored inside the battery, and then it gets transformed into electrical energy as it runs through the wires, and then it reaches the light bulb and is transformed into internal energy. The light bulb gets hotter, and radiant energy, the energy shines out in the form of light. Now, if no light or heat is able to escape this box, then it'll just get trapped inside. The air inside the box will get gradually hotter and hotter, but the energy will not be able to escape. The total number of joules inside the box will stay the same, regardless of what form the energy happens to be in. So next we want to talk about work. Work is abbreviated with a capital W. And it's basically a measurement of how much energy gets transferred or changed. If you think of energy as money, then work is like a paycheck. When you get a paycheck, it has a certain dollar amount, like the place that you work for is giving you this amount of money. Work is the same sort of thing. If you do a job, work tells you how many joules of energy you're spending to do that job. So as a result, work has the same units as energy. Kilograms times meters squared per second squared, or Newton meters, or joules. Any of these are acceptable units for work and energy. To calculate work, we multiply force times displacement. This is if you're applying a force to move an object. The amount of work that it takes to move that object is equal to the force multiplied by the displacement through which you move the object while you're pushing or pulling on it. Now this is very important. In order for physical work to be done, 3 criteria must be met. The first is that there must be a force applied. No force, no work. Second, this force must cause an object to move. So I can push against a wall all day, but if the wall doesn't move, then by the physics definition, I haven't done any work. And third, some component of this applied force must be in the same direction as the motion. And we'll look at some examples of this in just a little bit and try to figure out whether work is being done or not and how much work is being done. All right, so take a look here. Here we have a man that's trapped inside a box. How did he get inside the box? I don't know. It doesn't matter. He's pushing against the side of the box. Is he doing work? Well, he is exerting a force, so the first criteria for doing work is met, but the box isn't moving. And so therefore, no, he's not doing any work. He may get very tired, he may feel like he's done lots of work, but unless he causes something to move, then by the physical definition of work, he hasn't done any. In the second situation, this man is much more fortunate. He's not inside the box, he's outside. And he's pushing against the box and causing it to move. So yes, this man is doing work. There's a force, there's movement, the force and movement are in the same direction, so work is being done. Now this is a tricky one. This will throw off a lot of people. Here the man is carrying the box, so he's applying a force upward to hold the box, but that's not the direction the box is moving. The box is moving forward. So yes, there's a force being exerted. Yes, the box is moving, but the box is not moving in the same direction that he's exerting the force. So this actually does not count as physical work. So let's look at some skill practice questions to make sure we understand these concepts. Suppose I'm holding a book whose weight is 25 newtons. Am I doing any work? Well, I don't even need to write anything down. The answer is no, I'm not doing any work. Because if the book isn't moving, if I'm just holding it steady, then it doesn't matter how much the book weighs. The displacement of the book while holding it steady is 0. So any force times 0 displacement is going to equal 0 work. All right, here's one. How much work am I doing if I lift a box weighing 125 newtons from the floor to a height of 1.8 meters? Right? No, we'll use the formula for work. Work is equal to force times displacement. The force that you have to use to lift a box is equal to the weight of the box. So for F, we will plug in 125 newtons, and the displacement is just the height to which we lifted the box, so we'll plug in 1.8 meters. And if we multiply those two numbers together, 125 times 1.8 it gives us 225. Now we're only allowed two significant figures, so we can either write it as 230 without a decimal point, and for the units we could put Newton meters, or we could just simplify and say joules. Or if we don't want that non-significant zero, we could also write 2.3 times 10 to the second joules. And it's all the same, so it doesn't really matter which one you write. All right, here's another one. How much work am I doing if I apply a force of 45 newtons at an angle 20 degrees below the horizontal to move a book 0.75 meters across the tabletop? All right, you'll notice that the force is being applied at an angle below the horizontal. So there's two components to this force. One component is vertical, and this vertical component doesn't actually do any work because the book is not moving in a vertical direction. World's best arrow right. The other component, horizontal component, is actually doing work because the book is moving horizontally. No, I take it back. That's the world's best arrow right there. In any case, we are interested in finding out the horizontal component of the force, and then we will use that horizontal component to determine how much work is being done to move the book. Now, the horizontal component is adjacent to that 20-degree angle, so we will use cosine to figure out the horizontal component. We will say that the cosine of 20 degrees is equal to, and it's going to be the adjacent divided by the hypotenuse. So the adjacent, we will call that FH for horizontal force, and then the hypotenuse is 45 newtons. Multiply both sides by 45 newtons. So 45 newtons multiplied by the cosine of 20 degrees gives us our horizontal component. And you punch that into your trusty calculator, and you find out that the horizontal component to two significant figures is 42 newtons, which is almost the same as 45 newtons because this force is almost horizontal. It's just a little bit less. So now we're going to use that force and plug it into work is equal to force times displacement. The force, of course, is a force is a force, of course. The force is 42 newtons multiplied by the displacement, which is 0.75 meters. And when we multiply those two numbers together, we find that the work done is 32 joules. Round it to two significant figures. So that's going to be it for lesson 6.1. Come back tomorrow when we'll go into lesson 6.2, which is all about power. Looking forward to it. I hope you have a great day. Stay safe. Keep washing your hands. Talk to you tomorrow. Bye.